Welcome back, scholars. In this video, our final one for this paper, we tackle question 5 of the BBIT300, also cross-listed as BIT3201A Data Mining and Data Warehousing, sat in April 2019. Question 5 is worth 20 marks and it is the last of the optional questions. It covers machine learning fundamentals and a full worked ID3 decision tree. Part A contrasts supervised and unsupervised learning. Part B distinguishes classification from prediction. Part C describes the two phases of decision tree generation. And Part D, worth 10 marks, asks you to run the ID3 algorithm by hand on the classic laptop buyer dataset to build a decision tree that predicts who will respond to a special offer. Part D is half the marks, so we'll spend most of our time there. Let's begin. Here is the roadmap. Question 5 has 4 parts, 20 marks in total. Part A, 4 marks, asks you to characterize supervised and unsupervised machine learning and explicitly point out their mutual differences. Part B, 4 marks, asks you to distinguish classification from prediction as forms of data analysis, using examples. Part C, 2 marks, asks you to describe the two phases of decision tree generation. And Part D, 10 marks, the big one, gives you the classic laptop buyer dataset, 14 rows of customer details, and asks you to use the ID3 algorithm to build a decision tree that predicts who will buy. Parts A, B, and D carry 18 of the 20 marks between them, with the ID3 worked example alone worth half the question. So that's where the bulk of your time goes. Part of 4 marks, supervised learning works on labeled data. You hand the algorithm a set of training examples where each one already carries the correct answer, the class label, and the algorithm learns a mapping from the inputs to that label. Classic tasks are classification, predicting a category, and prediction, predicting a continuous number. Unsupervised learning works on unlabeled data. There is no target answer. The algorithm must discover structure on its own, grouping similar items into clusters or finding the principal axes of variation. The classic task here is cluster analysis, like k-means. Now the differences explicitly. First, the data, supervised uses labeled, unsupervised uses unlabeled. Second, the goal, supervised predicts an outcome, unsupervised discovers hidden structure. Third, the feedback, supervised has a known target to check against, unsupervised does not. And fourth, the evaluation, supervised uses accuracy and error rate, unsupervised uses cluster cohesion and separation. State all 4 and you have the full 4 marks. Part B, 4 marks, distinguish classification from prediction using examples. Both are forms of supervised data analysis, but they differ in what they output. Classification predicts a categorical label, a discrete class. The output is one of a fixed set of categories. Example, given a customer's age, income, and credit rating, classify whether they will buy a laptop. The answer is yes or no. Other examples are spam detection, where an email is spam or not spam, and disease diagnosis, where a tumor is malignant or benign. Prediction, sometimes called regression, predicts a continuous numeric value. The output is a number on a scale. Example, given a house's size, location, and age, predict its selling price. The answer is a number like $420,000. Other examples are forecasting tomorrow's temperature or predicting a student's exam score. The core difference: classification outputs a category, prediction outputs a number. The algorithms differ: 2 decision trees and naive Bayes for classification, linear regression, and neural networks for prediction. Part C, 2 marks, describe the two phases of decision tree generation. Decision trees are built in 2 distinct phases. Phase 1 is the tree building or growth phase. Starting at the root with the full training set, the algorithm recursively splits the data. At each node, it chooses the attribute with the highest information gain, the one that most reduces the entropy of the class label, partitions the data on that attribute's values, and repeats on each subset. Splitting stops when a subset is pure, when no attributes remain, or when no split improves purity. The output is a fully grown tree that may perfectly fit the training data but overfit it. Phase 2 is the tree pruning phase. To fight overfitting, the algorithm simplifies the tree by removing branches that add little predictive power, collapsing subtrees back into leaves. Pruning uses a separate validation set or statistical tests, and the result is a smaller, more general tree that performs better on unseen data. Build it big, then trim it back. That is the 2-phase recipe. Now Part D, 10 marks, the ID3 worked example. Here is the dataset collected in an electronics shop. 14 customers, each described by 4 attributes, age in 3 bands, income as high, medium, or low, whether they are a student, and their credit rating as good or bad. The class label is whether they bought the laptop, yes or no. 9 of the 14 bought, 5 did not. The task is to use the ID3 algorithm to build a decision tree that predicts who will respond to a future offer. ID3 builds the tree top-down, recursively. At each node, it computes the information gain of every remaining attribute. That is the total entropy of the node minus the weighted entropy after splitting on the attribute, and it picks the attribute with the highest gain. It then partitions the rows on that attributes values and recurses on each branch, stopping when a subset is pure. On the next slide, we compute the very first split, the root of the tree. Slide 7, the root selection. First, the total entropy of the class label, 9 yes, 5 no out of 14. The entropy is minus 9/14 log 2 of 9/14, minus 5/14 log 2 of 5/14, which evaluates to approximately 0.94 naught bits. Now compute the information gain for each of the 4 attributes. For age, splitting into the 3 age bands leaves a weighted entropy of about 0.694, so the gain is 0.940 minus 0.694 equals 0.247 bits. For income, the gain is only 0.029, almost nothing. For student, the gain is 0.152. And for credit rating, the gain is 0.016, the weakest of all. Age has by far the highest information gain at 0.247 bits, so age becomes the root of the tree. The dataset partitions into 3 branches, under 31, 31 to 40, and over 40. On the next slide, we recurse on each branch. Slide 8, build the tree by recursing on each age branch. First, the under 31 branch, 5 rows, 3 no, 2 yes, so not pure. Among the remaining attributes, student gives a perfect split with information gain of 0.971 bits, so we split on student. Of the 3 who are not students, all 3 said no, pure leaf, predict no. Of the 2 who are students, both said yes, pure leaf, predict yes. Second, the 31 to 40 branch. 4 rows, all yes, already pure. No further split needed. This becomes a leaf that simply predicts yes. Third, the over 40 branch. 5 rows, 3 yes, 2 no, not pure. This time credit rating is the perfect split, again with gain of 0.971 bits. Of the 3 with bad credit, all 3 bought leaf, predict yes. Of the 2 with good credit, neither bought leaf, predict no. So the full tree is age at the top, under 31 splits on student, 31 to 40 is a yes leaf, over 40 splits on credit. Every leaf is pure, so the tree is complete. Slide 9, the final decision tree. Here it is in full. At the root, age, 3 branches, left branch, age under 31, test student. If not a student, predict no. If a student, predict yes. Middle branch, age 31 to 40, predict yes directly, no further test. Right branch, age over 40, test credit rating. If bad credit, predict yes. If good credit, predict no. And that is the answer to Part D, a decision tree that correctly classifies all 14 training examples. Read it like a flowchart. Start at age, follow the branch that matches the customer, and at each inner node test the next attribute until you hit a leaf which gives the prediction. A young student with good credit, age under 31, then student equals yes, so predict yes, they will buy. An older customer with good credit, age over 40, then credit equals good, so predict no, they will not. Memorize this structure. It is the textbook ID3 result. Slide 10, a quick recap of the formulas and the method, because these are what you write down in the exam. The entropy of a set S with C classes is minus the sum over each class of P sub I log 2 of P sub I, where P sub I is the proportion of S belonging to class I. Entropy is naught when the set is pure, and 1 when the classes are evenly split. The information needed after splitting S on attribute A is the weighted sum of the entropies of each subset produced. And the information gain is the total entropy of S minus that weighted information. Pick the attribute that maximizes it. The recipe in 4 steps. 1. Compute the total entropy. 2. Compute the information gain for every remaining attribute. 3. Pick the attribute with the highest gain and split on it. 4. Recurse on each branch and stop when a subset is pure. That is ID3 in a nutshell. Let's lock in the takeaways for question 5. First, supervised versus unsupervised. Supervised learns from labeled data to predict an outcome. Unsupervised learns from unlabeled data to discover structure. They differ in data, goal, feedback, and evaluation. Second, classification versus prediction. Both are supervised, but classification outputs a category by or not by, spam or not spam, while prediction or regression outputs a continuous number like a price or a temperature. Third, the 2 phases of decision tree generation. Build the tree by recursively splitting on the highest information gain, then prune it back to fight overfitting. And fourth, the ID3 worked example. The root is age because it has the highest information gain at 0.247, under 31 splits on student. 31 to 40 is a pure yes leaf, over 40 splits on credit. Every leaf is pure, so the tree classifies all 14 training examples correctly. Memorize these 4 points and question 5 is fully covered and with it the whole paper. That's all 5 questions revised. Until next time, keep studying and good luck in your exam.